Good morning, everyone. I'm Peter Vermeulen, a geophysicist working with OptiSeis Solutions Limited. Welcome to GeoConvention 2022's Seismic Acquisition Session. Today, I'm going to talk with you about acquisition footprint reduction. The data and analysis is a showcase of EcoSeis Phase 1, a project OptiSeis has completed with their joint partners within COSIA. The title of my talk is Lean Green Seismic Imaging Machine. The lean green is in reference to our goal of reducing acquisition footprint and GHG emissions. Seismic Imaging Machine is a tip of my hat to Andrea and the rest of the OptiSeis team who, after creating, analyzing, and interpreting over 24 new geometries, have started to feel like seismic imaging machines.
So where are we going today? I'll start by taking a brief look at the history of low-impact seismic, then review some geophysical technologies that have been developed since we started using LIS. I'll speak to the impact those technologies have had on both seismic surveys and the environment. Then we'll jump into the EcoSeis project and talk about developing lean green geometries, touch on how we're ensuring success. Then I'll show some of the learnings within the project, go over the conclusions, and show what we have planned for EcoSeis Phase 2. Who's monitoring our footprints? As it turns out, the Alberta Human Footprint Monitoring Program is. This project is a collective of government agencies, industry associations, and not-for-profit institutes working together to quantify all human footprints in Alberta. This graphic is from their 2021 updated report on the history of seismic exploration in Alberta. They detailed how government, industry, and forestry all work together to transition from high impact to low impact seismic in the early 2000s. If you're as old as I am, you'd have had the chance to witness firsthand what high impact seismic was like. Clearing 6 to 8 meter wide cut lines with the dozer blade, frequent blowouts, standing water. Thankfully, as an industry, we transitioned to low impact seismic where line widths were reduced, duff layers preserved, and predator sight lines eliminated. How was this possible? Well, two things, mulchers and satellite GPS. Satellite GPS has allowed mulcher operators to be guided by the program's survey files. They know where they're going at all times and use discretion to avoid old growth and ensure a meander in the lines. Today, we've reached LIS's 20th anniversary, celebrating these initial adopters who achieved several monumental benefits. LIS reduced acquisition footprints between 50 and 60% in Northeast Alberta's boreal forests. Safety was greatly improved as mulch lines removed pokers, the unwieldy trees, branches, and stumps that endanger people and equipment. Mulch was viewed as environmentally responsible and was thought to protect soils and retain moisture. But the bottom line is, LIS enabled geophysicists to transition to high-density, high-resolution surveys by providing large cost efficiencies via predictable, well-groomed cut lines. 20 years ago, new technology enabled us to reduce our footprint by over 50%. What technologies are helping us do it again today? Our go-to sources like mini-vibes and buried pentolite explosives are now being replaced by miniaturized sources that deliver the same bandwidth at the same interval spacing, but only require 1.75 meter wide lines. Cabled recording systems that needed large trucks to move around are now cableless and can be moved by ATVs and snowmobiles. Development in the node space has already replaced wireless recording systems for deep targets and is on pace for high-frequency, shallow target recording in the near future. Simultaneous acquisition and the processor's ability to D-blend shot records is another big leap for efficient seismic acquisition. And as the EcoSeis Phase 1 has discovered, advances in 5D interpolation algorithms are predicting missing offsets and azimuths using a neighborhood of acquired seismic traces. What's the impact of these new technologies? Essentially, a trace density explosion, which is resolving our subsurface targets more clearly than ever before. The message has been loud and clear. More is better. Today we pause to ask, is more better? From decades of ecological research, the answer, with regard to Alberta's northern boreal forest, is a pretty obvious no. Here, we take a tour of 50 square kilometers of high-density seismic, some of which is over 8 years old. Let's take note what the ecologists have discovered through their research. High-density orthogonal seismic cut lines fracture the forest. In all but the highest uplands, these cut lines are extremely slow to regrow. The cut lines disturb habitats, which in turn disrupts predator-prey relationships, which leads to imbalanced species populations. The cut lines also contribute to increased GHG emissions through the removal of canopy and soil compaction. The good news? Industry has begun the process of reclamation, but one thing is clear, it comes at a very high cost. How can we achieve the same footprint reduction as LIS brought us 20 years ago without sacrificing current data quality? Conventional LIS with 2.75 meter wide source lines and 1.75 meter wide receiver lines requires us to cut about 8% of the total program area. If we use miniaturized sources and reduce the source line width to 1.75 meters, we can achieve a 22% footprint reduction. Definitely a good start. Now, what about removing receiver lines altogether? Yes, it's been done. We call this a megabin geometry. But in order to maintain similar data quality, line spacing needs to be decreased. The megabin geometry with 2.75 meter wide cut lines is an 8% footprint reduction from the orthogonal geometry. If we use miniaturized sources, we can reduce the total disturbed area in the program by 42%. Now we're starting to get close to footprint reductions we saw 20 years ago. But these lean green geometries need to work as baselines and on existing 4D surveys. Line spacing needs to match existing surveys to avoid new cutting. So we ran calculations for a few meandering linear geometries at 60 meter spacing. By increasing the line spacing compared to megabin, we can start to see footprint reductions stretching past 50% when moving to 1.75 meter wide lines using miniaturized sources. The question now is what happens to the imaging quality? That's where EcoSeis Phase 1 begins. How did we create and test new geometries? We were fortunate to have started with a well-sampled oil sands grid dataset. 20 meter receiver and source line spacings and 20 meter source and receiver station intervals. We decimated that to a symmetric 60 meter orthogonal geometry, suitable for shallow oil sands targets, and used that geometry as a baseline reference. We then decimated to a 40 meter megabin geometry to further explore the megabin's strengths and weaknesses. Initially, we wanted to push the limits of these linear geometries to get an understanding of where the breaking points were. So a tightly spaced but sparsely sampled 40 meter hexagonal geometry and sparsely spaced, sparsely sampled sinusoidal geometry were created for comparison. Later in the project, Realizing line spacing, source and receiver distribution, and the ability to match existing surveys were critical components to our future success. We created a 60-meter zigzag geometry that matched the line spacing and trace density of the orthogonal 60-meter geometry. Design analysis was run for each geometry to compare Fresnel fold, trace density, offset, and azimuth distribution, and fold tapers. The goal of the project was to maintain or increase data quality. So our due diligence to validate these lean green geometries included extensive QC through the processing and interpretation of the decimations. In EcoSize Phase 2, we will be performing quantitative analysis, and the best geometries that pass the processing and interpretation QC will go through this. All our processing flows were to AVO compliant pre-stack time migration in preparation for EcoSize Phase 2. With over 20 decimated geometries to choose from, a quick and cost-efficient processing flow was needed. The EcoSize geometry candidates first went through pseudo-processing. Here, the decimation was conducted before migration, borrowing velocities, statics, and noise attenuation from the undecimated dataset. Geometries that passed were then selected for full processing, which saw the decimation performed from raw shots. Unique velocities, statics, and noise attenuation were applied. Only after passing the processing and interpretation QCs was the fully processed geometry branded EcoSize. Throughout the processing, we discovered not all 5D interpolation is created equal, and working with a company that understands, or better yet, creates their own algorithms really helps when creating unconventional geometries. Here we see the 5D interpolation filling the gaps created by a decimated geometry, followed by a pre-stack time migration. In slice view, we can easily pick out if the 5D interpolation was doing its job. Here we see how the interpolation does a great job of filling the gaps. And after pre-stack time migration, the data cleans right up and edges become crisp with the energy positioned in the right place. The interpretation QC started with well-tie analysis. Next, we seed picked some key horizons and ran them through the auto picker for comparison. The volume was flattened and slices were examined at levels where depositional and structural imaging were important. To understand how the waveforms were impacted by the decimation, phase and frequency slices were generated and analyzed. Finally, NRMS was calculated between the decimated and non-decimated geometries to highlight where the differences occurred. Now let's jump into some results. We start by comparing the 60-meter orthogonal and 40-meter megabin geometry. The megabin was created with 10% higher trace density than the orthogonal. If we look at the shallow auto-picked horizons, we can see both geometries perform very well, as the time structures of both geometries are comparable to the grid geometry. Although the megabin amplitudes drop slightly, we can see that the details in the amplitudes compare well to the orthogonal and grid geometries. NRMS highlights the megabin's strengths and weaknesses. We see slightly higher NRMS away from the structure and within the bulk of the survey, but the orthogonal geometry handles structure and survey gaps a little better. The hexagonal and sinusoidal geometries were meant to look at two factors: trace density and meander amplitude. The surveys had similar trace densities, but drastically different footprint reductions. To obtain the same trace density, we used a weave pattern for the hexagonal geometry and alternating sources and receivers for the sinusoidal geometry. Both geometries performed poorly through the auto-picking, especially at the structural transitions. Amplitudes displayed a strong, shallow acquisition footprint, and there is a loss of resolution as seen by the smearing of key geological features. The NRMS ultimately confirms the geometries with low trace densities and large line spacings are not going to achieve our objectives of keeping image quality the same or better. The last geometries I want to show is 60-meter zigzag. It achieves an impressive 26% reduction in footprint with 2.75 meter wide lines and a 53% reduction in footprint with miniaturized sources. The auto-picked horizon recovers the time structure well, with only a few missed picks around the edges of the structure. The amplitude decreases slightly with a small loss of resolution. The NRMS, although higher, was an encouraging result and led us to further investigate different shot and receiver station patterns along the line and near the edges of the survey. We will save those results for after EcoSeis Phase 2 is complete. What we can conclude from EcoSeis Phase 1 data we reviewed today. We have explored how linear geometries are one way to reduce seismic acquisition footprints up to 50% from those footprints of a conventional LIS orthogonal geometry if we adopt newer source technologies. The megabin geometry produces great imaging, but is unsuitable for 4D repeat survey based on the line spacing requirements. And in order to maintain resolution when using linear geometries, both line spacing and source receiver distribution are the most critical variables to optimize. What are our next steps? Well, EcoSeis Phase 2 is already underway, and OptiSeis has started the qualitative interpretation work on several successful geometry options. Coming up this winter season, OptiSeis and their COSIA partners will move forward with a measured field trial in conjunction with one partner's previously planned seismic program. This test will measure the environmental performance of EcoSeis. How much can we reduce footprint and GHG emissions? The field trial will also quantify any potential cost savings and let us understand the operational efficiencies. Finally, and most importantly, the EcoSeis field trial will be the ultimate test to understand if we are able to maintain or even improve imaging quality.
With that, I'd like to acknowledge Synovus for sharing their data and expertise, Key Seismic for the processing and 5D interpolation discussions, OptiSeis for the geometry designs, interpretation, and analysis, and Alberta Innovates and COSIA for funding support. Finally, we'd like to thank the GeoConvention for the opportunity to present to you EcoSeis Phase 1.